Hey, Calculus, Mr. Florio again, 5.3 Riemann sums and definite integrals. I'm going to make this two videos. Hopefully they're not as long as the last ones. This guy right here, George Frederick Bernard Riemann, he was a big deal in the math community, and these Riemann sums are named after him. And you could read how his mathematics form the structure on which Einstein's general theory of relativity is based on. That's pretty impressive. Um, what we've been working with, this limit of, this sum, when we add up all these rectangles, is what we're going to call a Riemann sum. You could have that written down. I'm not going to have you write this down and talk much about this, but the argument that the next few pages in the book makes is that when we find the area under a curve, what we've been doing is say, let's make a bunch of rectangles, and if I want a good area, I need to increase the number of rectangles, right? So that area isn't going to give me the exact area. I've overshot it or undershot in some places. If I increase the number of rectangles, then I can get a better area. The idea of increasing rectangles is the same thing as the rectangles' width. In order for me to put infinite amount of rectangles in here, their width needs to get really small. So the norm is what we're going to call the width. The norm or the width of the rectangles has to approach 0 if you want to get infinite amount of rectangles in here. So that's what they're going to say here. They're going to have the norm or the width of each rectangle approach 0, and that's the same thing as what we've been doing. And this is what we're going to call a definite integral. A definite integral is the limit of the sum. So we take a Riemann sum and we take the limit as those rectangles get infinitely small, and that's what we call the definite integral of f from a to b. The number a is the lower limit of integration, and the number b is an upper limit of integration. Right now, this is just a notation that I want you to know is another way of writing a limit of a sum. This will, in the next section, relate back to antiderivatives, but right now, this is a notation that means take the limit of a bunch of infinitely small rectangles under my function between a and b. This is the same a and b that we've been working with. And we can, as long as the function is continuous and non-negative on that interval, then I can find the area of that function, because like we said before, this is going to give us area. As long as my function is positive and continuous, this definite integral will give me the area. So this tells me the area between the graph of f, so here's f, the x-axis, here's the x-axis, and the vertical lines a and b. So if I want it to be between the function, the vertical lines a and b, and the x-axis, this is the area that this definite integral will give me. Okay, so let's actually apply this in an example, and then we'll do more examples in the next video. Evaluating the definite integral as a limit. So I'm going to use that definition that you just copied down up there. I want to take the answer. This thing is equal to the limit as the width of each rectangle approaches 0. So they get really, really skinny. And if I add up all these rectangles from 1 to n of f of ci times delta x. What's delta x again? That's just b minus a over n. And we said that the integral is from a to b, so -2 is my a and 1 is my b. So that's going to be 1 minus -2 over n, which is really 1 plus 2, or 3 over n, is delta x. Ci, we can use a plus delta xi as a general formula. And a is -2. Delta x is 3 over n times I. Okay, so this, again, as the rectangles get infinitely skinny, that's we're going to say that's the same thing, and it's okay. As the number of rectangles goes to infinity, we'll just do it the way we've been doing it. And that's okay. So we're going to add up the sum of all these rectangles. Now, f of ci, let's see here. My function f of x is just 2x in this case. That's what f of x is. So my function just takes its input, x, and doubles it, multiplies it by 2. So that's just going to be 2 times ci, and we know ci is negative 2 plus 3i over n. So that is that part. And the delta x part is just times delta x, which is 3 over n. So that's delta x. Okay. We're going to clean this up and evaluate the limit. So this is the limit as n approaches infinity of the sum, where I goes from 1 to n. Let's see. 2 times 3 is 6. So I'm going to take 6 over n and distribute it in. 6 over n times 2 is negative 12 over n. 6 over n times 3i over n. 6 times 3 is 18. N times n is n squared. Okay. And now using our summation properties here, this is the limit again as n goes to infinity. So negative 12 over n is a constant. There's no i's in here for the index I. So this is just a constant. And when you're adding up a constant n times, that's just that constant times n. That's one of our summation formulas. This next one, 18 over n squared, is just a constant. And if I add I up from 1 to n, the formula for that was n times n plus 1 over 2. And let's see how this works out here. The n's are going to cancel out. That n will take out one of those n's. 18 over 2 is just 9. So I really just have a 9 over n here to distribute. So this is the limit as n approaches infinity. I have negative 12. Let's see, this is just 9 over n. 9 over n times n. 9 over n times n is 9n over n. And then 9 over n times 1 is just 9 over n. These will divide out. And as n goes to infinity, negative 12 won't be affected. 9 won't be affected. But as n goes to infinity, that's just going to get to be infinitely small. It's going to go to 0. So it's going to be just negative 12 plus 9, which is negative 3. So that's the answer. This thing is equal to negative 3. So pretty exciting there. What's this have to do with the price of pizza? I don't know yet. But one thing I want to mention before we go on is I said this is area under a curve. The function 2x is just, it looks something like this. Let's see, from 1, we're going all the way to negative 2. So from negative 2 to 1, here's the function. Negative 2, this will be negative 4, by the way. I can think of this as area. What's the area of this right triangle? The base is 1, the height is 2. So that area is 1/2 base times height, which is just 1. 1 times 2 is 2, half of 2 is 1. And the area in this little region here is 1/2 base. The base is 2. The height is 4. 2 times 4 is 8. Half of 8 is 4. We've always said area has to be positive, but if for a minute I say area above the x-axis is positive and area below the x-axis, we'll call that negative, then negative 4 and 1, when I combine those areas, is going to give me negative 3, which is exactly what we got as our answer. There's a relationship between the geometry area and the calculus area with this limit of a something. Anyways, we're going to use that idea of finding the area of geometric figures instead of doing the sum in the next few examples. All right, that's all.